Okay, so it's a pleasure to welcome our speaker today. It's Tim Susse from Bard College at Simon's Rock, and he's going to tell us something about geometric properties of random right-angled Coxeter groups. So, Tim, please.
Thanks, Ilya, and thank you so much for letting me speak today. I'm going to talk to you a little bit about a project that I've been working on for several years with Jason Bairstock, Victor Falgas-Ravary, and Mark Hagen on random right-angled Coxeter groups and trying to discern some generic properties of them. So I'll get started by talking a little bit about right-angled Coxeter groups. So given a simplicial graph gamma with vertex set V and edge set E, we'll have the right-angled Coxeter group W gamma, and it will be generated by the vertices of the graph. Each vertex will have order 2. It will be a reflection. And then we'll say that 2 vertices commute whenever they span an edge in the graph. So what we want to think about is we'll have V, that's generating like a Z mod 2, W, that's generating like another Z mod 2, and then these will commute if and only if V and W are joined by an edge. So the correspondence that assigns to each graph gamma a right-angled Coxeter group is 1-to-1. So we'll call W gamma the right-angled Coxeter group with generating graph gamma. And so since we have sort of a bijection between graphs and groups, we would hope that geometric properties or algebraic properties of the group are reflected in the combinatorial properties of the graph. So some examples of this, the right-angled Coxeter group is finite if and only if gamma is a clique. And by clique, another word for that is complete graph. So that every pair of vertices spans an edge. Another property is that we can decompose the right-angled Coxeter group as a non-trivial direct product if and only if gamma is a join of 2 subgraphs. So by join, we mean that we have 2 subgraphs, gamma 1 and gamma 2. And every vertex of gamma 1 is connected to every vertex of gamma 2. So every element of the subgroup generated by gamma 1 commutes with every element of the subgroup generated by gamma 2. And so this gives us a direct product decomposition of W naturally, but this is also the only way that you could decompose W as a direct product. So some more subtle properties. So the right-angled Coxeter group will be one-ended if and only if the graph does not have a separating clique. That is a complete subgraph, where when you remove the complete subgraph, you get a disconnected graph. And a famous result of Mousson is that a right-angled Coxeter group is hyperbolic if and only if gamma does not contain any induced squares. And this is really important for us today. So I just sort of want to explain a little bit where this comes from. So if we have a square, an induced square, so that means a square where you don't have any of the diagonals, this generates a subgroup. Well, let's see. What we have here is we have the square is a join of 2 discrete graphs. So what we've got here is Z mod 2 free product Z mod 2 from the first discrete group. We've got a Z mod 2 free product Z mod 2 coming from the yellow discrete subgraph. And then it's a join of these, so we get a direct sum, so we get a direct product. But of course, Z mod 2 free product Z mod 2, that's the infinite dihedral group, and that's virtually Z. And so this subgroup here, this is virtually Z squared. And so what Mousang's result is really saying is that a right-angled Coxeter group is hyperbolic if and only if it does not contain z squared. One more here, and we'll talk about this in a little more detail. So a right-angled Coxeter group has linear divergence if and only if gamma is the join of two non-cliques. And so linear divergence here, you can think of this as saying the asymptotic cone of W does not contain any cut points. So I mentioned divergence, so I should define it. We'll do it in 2 steps. So let's start with a geodesic metric space, X. And we'll have a parameter rho that can be anywhere from 0 to 1. So for a triple of points, A, B, C, and X, where the distance from A to C is R, and the distance from B to C is R, we're going to let this D sub rho R C of A, B. So what we're going to think of this as is the avoiding distance. It's going to be the infimum of lengths of paths from A to B that stay outside the ball of radius rho times R from C. So right here, we've got the ball of radius rho R, and we want to look at all the paths from A to B that stay outside of this ball. And we're going to take the infimum of the lengths of all of these paths. So we can think of this as the distance from A to B in the metric space obtained by removing the ball of radius rho R around C. So the divergence of a geodesic metric space is going to be a collection of functions. For every row, we're going to have a different function. So it's going to be divergence with this parameter rho of R. It's going to be the supremum of all of these avoiding distances over all triples A, B, and C, and X, so that the distance from A to C and the distance from B to C are both R. In essence, what we're doing is we're tracking the worst case scenario for the length of a path avoiding a ball of radius rho times R. So when we consider the divergence, we won't consider that function precisely. We'll use our usual equivalence for functions. So we'll say that 2 functions f and g are equivalent if there is a c greater than 0, so that f of r is less than or equal to c times g of cr plus c plus cr plus c, and similarly reversing the roles of g and f. So we'll consider the divergence function up to this equivalence relation. So some important facts about the divergence function. First, if x is a cat 0 space, then we don't really need this parameter rho. The divergence with parameter rho is equivalent to the divergence with parameter 1. And so we can just talk about the divergence function as just this divergence with parameter 1. And very importantly, if x and y are quasi-isometric, then their divergence functions are quasi-isometric, at least up to adjusting your rows, if that matters. So some prior results about divergence. So if x is cat 0, then x has either linear or at least quadratic divergence. And so this is a result of Kapovich and Lieb from 98. X has more than one end if and only if its divergence is infinite. So if x has more than one end, then we're going to be able to remove a compact ball that will disconnect our space. And so we'll get 2 points that are infinitely far apart, where there is no path between them that avoids a ball of radius r, rho r. And so we'll get infinite divergence in that case. And that's really the only way we can get infinite divergence. So very importantly for us, if x and y are unbounded metric spaces, then the divergence of their direct product is linear. And so we can think about this as basically, you can just move in one of the components far enough away, then move in the other. You sort of move in x and y separately, and you're going to be able to avoid a ball of radius r very, very easily. So results of cysto, so that if X is a relatively hyperbolic group, I should say, or I guess a relatively hyperbolic metric space, then its divergence is exponential. And a very important result of Truchu, Moses, and Sapir from 2010 tells us that metric space X has linear divergence if and only if none of its asymptotic cones have cut points. And so in terms of what you can get for divergences, so it's a folklore that Gromov at some point suggested that all one-ended finitely generated groups have either linear or exponential divergence. But in '94, Gersten proved that there is a cat0 free bicyclic group that has quadratic divergence. Going in that same vein, Natasha Makura in 2002, and then a second result in 2013, proved that there are free bicyclic groups and cat0 groups where the divergence is r to the n for any natural number n. So Makura produced polynomial divergence of arbitrary degree. And Dunny and Thomas independently produced right-angled Coxeter groups that have a divergence of arbitrary degree. Okay, thanks, Jason. Yeah, so Jason pointed out that it's not a folklore question. It was asked in Gromov's paper, Asymptotic Invariance of Infinite Groups. And so if we want to know sort of what are some monsters, we go to this paper of Olshansky, Osen, and Sapir in 2009. They produced examples of groups that have subquadratic but superlinear divergence. And they're able to produce the sublinear divergence as close to linear as they'd like. Okay, so let's get back on track now with the divergence of right-angled Coxeter groups. So given a graph gamma, we'll form an auxiliary graph, the square graph of gamma. So its vertices will be in one-to-one correspondence with the induced squares of gamma, and two vertices will be joined by an edge if and only if the corresponding squares intersect in at least two non-adjacent vertices. So here's our graph gamma. So here's a square S in gamma.
What is this graph called, by the way?
So it's the square graph of gamma. Okay. So square of gamma. Thanks. So we'll start with this vertex S1. So we start with that first induced square. And then we see another induced square. S2, this green square. And we see that it intersects S1 in this diagonal. So in the square graph, S1 and S2 will be joined by an edge. And then because we've actually got a complete bipartite graph here, we actually have a third square that intersects both S1 and S2 along that diagonal. So we've got another square S3 in there. And S3 is joined to both S1 and S2. And we're not quite done yet. We've got some more squares to work with. Let's see, I might be running out of zoom colors here. So if we look at this very elongated square going down, S4, and we see that S4 is joined to S1 by a diagonal, this diagonal, but it is not joined to either S2 or S3 along a diagonal. And so S4 is joined to S1. And then similarly, we've got one more square here that's joined to both S1 and S4. So we've got an S5 there. And S5 is joined to both S1 and S4. So in this case, we get a square graph that looks like two triangles joined along a single vertex. So what this is keeping track of is keeping track of the squares in the graph and when those squares intersect along two non-adjacent vertices. So a theorem of Dunny and Thomas, and also later Levkovitz, tells us that if gamma is a simplicial graph, then the right angle Coxeter group W gamma has quadratic divergence if and only if gamma is a join of gamma prime and K, where K is a clique. So that corresponds to some finite subgroup that we can just sort of tear off. And gamma prime is not a non-trivial join. And there's some component of the square graph of gamma prime so that the union of the squares from that component cover all vertices of gamma prime. So we've got our graph here, we've got our graph gamma over here. And now we've got our square graph gamma, or the square graph of gamma, and that may have multiple components. So it may have like a huge component, C1, and then a little component, C2, and a little component, C3. But all of these correspond to collections of squares inside of gamma. And so if we look at the union of all squares from C1, we look at what that union is. We look at, say, the union of all squares from C1.
But wait a minute, but C1 is in the other graph. It is in the square graph, right?
It's in the square graph. So each vertex of C1 corresponds to some square that sits inside of gamma.
Mm-hmm.
Right? And so we can look at the union.
What do you mean when you say union of squares from C1? Like,
so I mean, I want to look at what vertices are contained in squares that are squares that correspond to vertices in C1.
Okay. So what vertices of gamma are contained in squares which correspond to vertices of C1?
Yes, exactly.
Okay.
Yeah.
Mm-hmm. Okay.
Yeah. And so we want every vertex of gamma, effectively every vertex of gamma, to be contained in some square inside of a single component inside of C1. And maybe C2 and C3 don't have. And that's okay. We just need one component that has this property. And so we'll call such a graph CFS. And so for me, CFS says it means constructed from squares. So originally, Dunny and Thomas named this component with full support, but since then we've renamed it constructed from squares. Okay, and so just to give you an idea of how this proof works, what's going on here is that every square inside of gamma corresponds to a z squared subgroup, right? And so what we've got inside the Cayley graph are a bunch of flats, right? So if we're looking at the Cayley graph of W gamma in our generating set, the vertex set of gamma, what we'll see inside of there, every square will correspond to some flat inside of there. And then, so here we'll have some square. So we'll have a square in gamma. And that corresponds to some flat inside the Cayley graph. And then if we see that two squares are joined along a, let's say we have two squares that are joined along a diagonal, what we have are two z squared subgroups that intersect along a z subgroup. And so what we've got here is we've got these flats are sort of forming a network here. And maybe there's another flat that comes in over here. But the square graph is telling us about these networks of flats inside the Cayley graph of the right angle Coxeter group. And having a component of full support tells us that this network of flats fills up all of the group. So you can get anywhere in the Cayley graph that you'd like by traveling inside of this network of flats. And so this corresponds to a property called being thick of order 1. And so it's a theorem of Baerstock and Drutu. That a group that's thick of order 1 has at most quadratic divergence. And so that's sort of one of the steps in the proof here, sort of a visual understanding of why you would expect some property like CFS to encode quadratic divergence. And in fact, it does it. The theorem of Donny and Thomas and Levkovitz tells us that it does so precisely. And just sort of a note that will come into play a little bit at the end of the talk. There's, in fact, a strong dichotomy in right-angle Coxeter groups. This was proved by Baerstock, Hagen, and Sisto. A right-angle Coxeter group is either relatively hyperbolic or thick. And so consequently, it has either, a right-angle Coxeter group has either infinite divergence if it has more than one end, exponential divergence if it's relatively hyperbolic, or divergence that's bounded above by a polynomial in the case that it's thick. And you can get a slightly stronger result. Very recently, Levkovitz proved that in fact, you can replace bounded above by a polynomial by precisely polynomial divergence. So the question that all of this raises is, well, how common is quadratic divergence in right-angle Coxeter groups? Is this something that is just, you see there are just a couple of graphs, or is it something that you see all the time? Or equivalently, you can ask, well, how common is CFS among graphs? So that's the question we tried to answer. So to understand what we mean by how common, we need a model to produce graphs and talk about generic properties. And the model we use is was introduced by Gilbert, and then it's called the Erdős-Rényi model of random graphs. So it works as follows. So we'll fix a function P that goes from the natural numbers to the interval from 0 to 1. It's called the density. And so we obtain a probability space, GNP, of graphs with n vertices by declaring that 2 vertices are connected by an edge with probability P of n, independently of all other pairs. So you just have n vertices, they're labeled 1 through n or something, and anytime you see vertex I and vertex j, and you want to see if I and j are connected by an edge, well, that will happen precisely with probability P of n, where n is the number of vertices in your graph. And so when we have a random graph with these parameters, we'll say that gamma is sampled from GNP. We'll write gamma and then twiddle GNP. So we say a property P of graphs occurs asymptotically almost surely at density P if for gamma sampled from GNP, the probability that gamma has the property P tends to 1 as n goes to infinity. So large graphs tend to have this property almost surely.
Sorry, could you go back to the definition? I didn't quite understand.
Yeah, sure.
So the probability in your model, this P, I mean, is it the uniform probability or?
Yeah, so it's uniform for all pairs. So the only thing that matters is how many vertices your graph has. So we'll have like vertices 1, 2, 3,
okay,
and up to n. We start with n vertices in a graph, and then for any 2 of them we choose, I and j.
Okay, so that's what they're doing. Okay, I just wanted to make sure that that's what's happening.
Yeah,
okay.
yeah.
There's a number of vertices, and okay, got it.
Yeah, yeah. You for every pair of vertices, you flip a coin, and to decide if they're connected by an edge. But your coin lands on heads with some probability that depends on n. Okay, so some well-known theorems from the theory of random graphs. So for any epsilon greater than 0, if your density is at least 1 plus epsilon log n over n, then asymptotically, almost surely, a random graph at density p is connected. But if your density is less than 1 minus epsilon log n over n, then asymptotically, almost surely, your graph is disconnected. And so there's a very drastic change of behavior that happens at the density log n over n. And such behavior is called a sharp threshold. This is a sharp threshold for connectedness. And then it's one of the results that sort of motivated the study of random graphs initially. There are other types of thresholds that we can get, and one that sort of will pop up for us a little bit. So if you take a positive integer r, then if your density is much, much larger than n to the minus 2 over r plus 1, so this means just that if you take p and you divide it by n to the minus 2 over r plus 1, that fraction goes to infinity, then goes to infinity. So it's much, much larger. Then asymptotically, almost surely, a random graph sampled from GNP contains a clique of size r. But if your probability is much, much smaller, little o, of n to the minus 2 over r plus 1, then it asymptotically almost surely contains no r clique. And so this is sort of a weak threshold. And this is common when you're thinking about subgraph inclusion. And so just some idea, I think a while ago, I used Mathematica generates Erdős-Rényi random graphs. You can just tell it, generate a graph and create a picture of it, and it will do that. And so I generated two graphs with 30 vertices. We'll see this one with higher density pop up again. So we notice that at sort of low density here, we've got this big component, and then we've got like a stray edge, but then a lot of isolated vertices. And this is actually very typical for low density graphs to have a lot of isolated vertices. But at higher densities, we notice that this thing is very connected. And so I think this was taken at density like 1/3. And we can see that, that we have lots of edges here and that this graph is actually highly connected.
Tim, I have a question. So can you think about this that way, that like you take this set of all graphs on n vertices and the subset of which satisfy like this probability? So because you said that we're talking about the probability space, it is a set of all graphs with n vertices, right?
Yes.
But so some of them are kind of are good graphs. They satisfy like this probability like for the edges. Okay.
Yeah, so what happens is that, so if you have a graph, so the probability distribution that this puts on the set of vertex labeled graphs with n vertices. So if you have a graph gamma, then it occurs with probability p to the number of edges of gamma times 1 minus p times, I guess this would be n choose 2 minus the number of edges in gamma. And so this gives you, that's the probability that you would choose gamma randomly.
Like so for example, the first graph on the first picture, what is P?
I forget exactly what I set P to be in that one. It's probably something like 0.1 or something, but a fairly low density of edges for 30 vertices. Yeah, I generated these a while ago, so I can't remember precisely what their densities were, but right. So what I did was Mathematica will just sort of it will generate, I guess, a pseudo random graph by taking pairs of. It will take the set from 1 to n. It will take all the subsets of size 2, and then it will choose those randomly, each one randomly with probability p. To be an edge, and then it will produce a graph from that.
But so basically out of all subsets of size 2, we select like p times.
You select each one, yeah, you select each one with probability p. Okay. And so you've got some sort of like binomial distribution going on here with the numbers.
It's like a Markov process, basically, like you go through subsets of size 2 and you're selecting like.
Yeah, exactly, but everything is independent.
Okay.
Every choice is independent of all previous choices.
Okay. Okay.
There are models of random graphs where there are dependencies, and I have many questions about this. So the main result that I want to share with you today is a sharp threshold for CFS. So for any epsilon greater than 0, if P of n is at least this terrible number, square root of the square root of 6 minus 2 plus epsilon times n to the minus 1/2. And the probability is not, the density is not too high. So it's not as high as 1 minus 1 over n squared. So express it this way. Then asymptotically, almost surely, a graph sampled in GNP has the CFS property. But on the other hand, if your density is less than this number, your density is less than this number minus epsilon times n to the minus 1/2, then asymptotically, almost surely, your random graph does not have the CFS property. And so this probability, the square root of 6 minus 2 times n to the minus 1/2, that's a sharp threshold for CFS in the world of random graphs. An immediate corollary of that is that if you take a random right-angled Coxeter group with density at least this number, then that right-angled Coxeter group will asymptotically almost surely have exactly quadratic divergence. But on the other hand, if your density is less than square root of 6 minus 2 minus epsilon n to the minus 1/2, then asymptotically almost surely it has at least cubic divergence. And so we get a sharp threshold for quadratic divergence in right-angled Coxeter groups. And actually an even stronger statement, below this threshold, you have at least cubic divergence. And so just to visualize what this sharp threshold looks like, Jason ran a program on a supercomputer that generated random graphs and then tested them for the CFS property. And so each one of these lines, each different color of line represents a different number of vertices. And then what you're looking at on the vertical axis is the proportion of the graphs that had CFS, the CFS property. What you're seeing on the horizontal axis is this parameter alpha. We were looking at densities alpha times n to the minus 1/2. And so what you see here is that sort of you're very low over here. Your probability of having CFS is like almost 0 over here where alpha is smaller. And then all of a sudden there's a sharp jump. And then the probability that you have CFS is almost 1. And so this is sort of what we use as this is how you can think about the sharp threshold. Very rapidly, graphs go from having very little chance of having CFS to a very, very high chance of having CFS. And so just if you want to sort of compare to the result before, our threshold occurs at square root of 6 minus 2. That's about 0.6704. And so you notice that actually that's somewhere over, it's not quite on the graph yet. But you might notice that as the number of vertices goes up, our lines are getting steeper, right? Where the change is happening faster, and they're also moving back a little bit. And so this had suggested to us that when we saw this graph, this suggested to us that yes, there was a sharp threshold. And it was somewhere in this range of like somewhere around 0.7, something like that. Okay, so just some prior results in this vein. So before we got started on this, Davis and Kale and also Charney and Farber, they used the Erdős-Renyi random graph model to obtain results about cohomology and outer automorphism groups of random graph products. And so in a slightly different vein than where we were looking. And so when we start looking at CFS, the first thing we notice is that the problem of deciding whether a graph has CFS is fairly delicate. And so what we did is in 2018, we worked to sort of pin down roughly where the threshold was. And so we sort of worked on in pieces for this CFS threshold. And so the first results from 2018, so with Jason, Victor, Mark, and myself, we showed that if your density is at least 5 times the square root of log n over n, and then this extra condition that your density is not too close to 1, then asymptotically, almost surely, your random graph will have CFS, and WGAM will have quadratic invergence. So we sort of, we knew that from 5 square root log n over n, and then going up almost all the way to 1, that we would have, the graphs would have CFS. And even in there, we sort of had to break down the interval farther. And so the first place we looked were at densities that were at least 1 plus epsilon cube root log n over n. And we showed that they had a stronger property that was called AS. And so just a little schematic picture of AS. So what's going on here is we have 2 vertices, V1 and V2, and we look at all of their common neighbors. So this generates some subgraph gamma prime. And so we look at all of their common neighbors. And so what we notice is that we have a lot of squares. For any pair of non-adjacent vertices in gamma prime, we have a lot of squares with diagonal V1, V2. And so this is called the UFO. And well, what we want the UFO to do is beam up all of the other vertices. And so the way that you beam up a vertex is that our vertex V that's not in the UFO, this is this little person over here, this person will get beamed up if it has as its neighbors 2 non-adjacent vertices inside the body of the UFO. Because then what we see is we see a square with diagonal V1, V2, and then let's call this W1, W2. And it's connected to a square that has the vertex V, the square V1, W1, W2, and V, or V2, W1, W2, and V, because of course one of these may be connected to V. And so if you have a UFO that can beam up all of the other vertices, then the graph will have CFS. I'll have the stronger property AS. And so, so for instance, that was our schematic picture, and this is our random graph before that I produced. And this graph actually has the AS property, and well, it looks a little bit different this time. The UFO is what I've highlighted here. So our vertices V1 and V2 are in green, and then the rest of the UFO is in red. And so we proved in 2018 that if your density is at least 1 plus epsilon cube root log n over n, then asymptotically almost surely gamma has the AS property, and hence the CFS property, but that actually cube root log n over n is the threshold for this strong property AS. And so that didn't get us all the way down to square root log n over n. We had to work a little bit harder than that. And so what we did, so we sort of had to beef up our AS argument or our AS construction to get down to this 5 square root log n over n. And so what we did is that, we chained together UFOs into a mothership. And so we would have, you would have one UFO, and then you'd find 2 non-adjacent vertices inside that UFO, and then you would produce their UFO. And then you would find 2 non-adjacent vertices inside that UFO, and you'd produce their UFO. And these are sort of getting smaller and smaller and smaller as you go. And so you do this n over log n many times, and then with high probability, each core is not a click. And then we show that every vertex will get beamed into at least one of these UFOs. And then to show that the graph is not in CFS, we show that the square graph at a low density, less than 1 over square root n log n, cannot contain a giant component, or a component that contains, no component of the square graph can cover more than log n vertices once the density is less than 1 over square root n log n. Okay, so summarizing where we were in 2018, we showed that if your probability was that we figured out sort of roughly where, we figured out that the threshold for CFS happens somewhere around n to the minus 1/2. So if your power was even a little bit more than n to the minus 1/2, then the graph would have CFS. The right angle Coxeter would have quadratic divergence. But if the power on your n was even a little less than minus 1/2, then almost surely gamma won't have the CFS property. So we in 2018, we pinned down that we needed to look around n to the minus 1/2, which is why we generated that graph, or why Jason had generated that graph that you saw earlier. So after our first paper, we knew roughly that the threshold was somewhere around n to the minus 1/2, but we wanted to know exactly where it was. And it turns out that this problem intersects with a big problem in percolation theory that was posed by Bolobash and Riordan. And so the idea is pretty simple. We've got our graph gamma, and we're producing its square graph. And what we want to do is start at a vertex V, and then we want to sort of try to explore the component of the square graph that contains V and figure out how large it is. Because a large component has a higher chance of covering all of the vertices. And so what we imagine is that we're going to branch out from V. And so we produce a whole bunch of new squares, right? V1, 1, V1, 2, et cetera, all of the neighbors of V inside the square graph. And then from each one of those, we then explore from there. We branch out from each one of these, and we look at their progeny inside of the square graph. And we get sort of a second generation of squares. And then we repeat, and we keep trying to explore more and more of that component by branching off of each one of the vertices that we find. And so this is we want to sort of model our exploration using a Galton-Watson branching process, which is just a fancy way of saying you try to find a spanning tree for the component. And so we're going to try to model this exploration using a branching process. And there are standard probabilistic techniques that we can use to analyze the success of this process. But as with all probability, that is not without its nuance and not without its complication. Okay, and so what we actually have to determine is exactly how much branching we can expect from a given vertex. So here we're going to look at a P. Our density is going to be some lambda times n to the minus 1/2, since we know our threshold's somewhere around there. So if we start with the square, and I'll draw it off to the side. Let's say ABXY. Then what we want to do is we want to find all of the common neighbors of X and Y in gamma. So we want to find all of their common neighbors, because all of their common neighbors will form a whole bunch of squares with that same diagonal XY. And so the number of common neighbors of X and Y is some random variable Z, which is distributed like a binomial distribution, where you have n-4 trials, and the success is p squared. The success rate is p squared because we need 2 edges to get a common neighbor. So 2 edges happen with probability p squared. Probability looks like lambda squared over n. Okay, but that's the number of common neighbors. We now need to analyze the number of new squares that we get from this branching process. So the number of new squares that we get, it looks like, well, we can take any pair of common neighbors of X and Y. That includes A and B. So we take any pair of them. and they'll form they'll form the opposite diagonal of another square. We actually already knew about our square, ABXY, so we subtract 1. So the number of new squares we get is z plus 2. We add back in a and b, choose 2 minus 1, which is 1/2 z squared plus 3/2 z. And then we can find the expected value of that. Z is a binomial distribution, and so we can just use sort of standard formulas for its expectation and the expectation of its square, its second moment. And so the expectation of the number of new squares that we get is given by this polynomial 1/2 lambda to the 4th plus 2 lambda squared plus some term that's going to go to 0 as n goes to infinity. Okay, so in a healthy branching process, you want to expect that each vertex has at least one progeny. That's how your branching process is going to survive. If no one has any kids, then the family tree stops. And so in a healthy branching process, our expectation should be higher than 1, at least 1 plus epsilon. But if the expected amount of branching is less than 1 minus epsilon, then this branching process will die quickly, right? Each branch will die fairly quickly because, well, you don't expect that many children at every stage. And so the whole branching process will die. And so what we figure out is that, well, the critical value will happen when this polynomial is equal to 1. And so we set this expectation equal to 1, and out pops our lambda, which is the square root of 6 minus. It has to do with when this branching process will survive, or the critical probability for this branching process. In case you were worried that where that number came from. Okay, so now let's sort of try to analyze this branching process. I'll give you a little idea of how this works. So let's first suppose that our probability is less than our threshold, so it's smaller than this critical probability. So we're going to start with a square S, and we're going to try to find all of its neighbors in the square graph of gamma. So we're going to do that by exactly what we were talking about before. We're going to start with ABXY. And then we're going to try to find all the common neighbors of X and Y, which will give us a whole bunch of new squares to play with. Then we have a whole bunch of new squares. And so we try to explore off of each one of these new squares that we just found. We try to now take one of the children's squares and branch off of that. But when we do that, we don't want to repeat any of the vertices that we've seen before. So what we're going to do is we're going to look for common neighbors that are new, that we haven't seen before. Vertices that we haven't discovered yet. And so this is sort of how we're going to model our branching process. But if we run out of untested squares, then we are going to look for, we may have missed some edges along the way because we didn't really care that much about any edges between vertices that we found. We only cared about common neighbors, but maybe this vertex here is joined to A. And maybe that creates some new square that we didn't know about before. And so we have some sort of correction procedure that we have to do to find any potential squares that we missed. And then we'll stop our process if we ever discover this horrible number of vertices. So, but the important thing is that it's a power of log n, many vertices. And so we'll call that a large stop to our process. We'll also stop if we need to correct too much. So if we find too many edges that we missed in our branching process, I think the number is 5. If we ever find 5 edges that we missed, we will stop. And that will be called a critical stop because we've accumulated too much dependency to continue. And if we run out of untested squares and there are no corrections to do, we will also stop. That's where the process just naturally dies. And that will be called, we'll call that a good stop, because the process will die as we want it to. And so what we had, so first off, if we start at a square S in our square graph and we do this exploration, if we end at a good stop, then we will discover all of the squares in the component of square gamma containing S. And in fact, we will discover many more, but it's okay, we're overcounting them. But the very important theorem is that actually with high probability, we almost surely do not, any exploration that we do, if P of n is less than our threshold, any exploration that we do will almost surely not end in a large stop or a critical stop. And so we almost surely always end in a good stop. So we almost surely always discover every square in that component. Oop. And so the corollary of that is that, well, if our density is less than the threshold, then asymptotically almost surely a random graph in GNP has no component of its square graph that covers more than power of log n many vertices. And in particular, that means it can't be in CFS. It can't be a CFS graph. It doesn't have, no component covers every vertex in particular. So that's sort of like a whirlwind tour of how we do the this is called the subcritical part, how we analyze the subcritical process. And so the supercritical process is a little more complicated. Things are a little bit delicate because we want all of our squares to be induced. And so if our density is too high, if it's larger than 5 log n over n, then we're gonna find squares, right? But there's a good chance that they'll have that diagonal. They'll have the diagonal, they won't be induced. And we don't wanna count these. And so we have to take care to only count the induced squares. And one way we can sort of make our lives easier is to assume that we have a density that's at least our threshold and at most 5 square root log n over n. And this is significant because that was the threshold that we had in our 2018 paper. Okay, so we explore as above, but now in our subcritical phase, we wanted to overcount the number of squares, and now we want to drastically undercount the number of squares and the size of a component. And this is just to avoid any dependencies along the way or accumulating too much dependence. So we'll start with the square S. We'll find all of its neighbors in the square graph, but we'll be careful to only count induced squares. And then we'll repeat the procedure with each new induced square we find. And the only time we'll stop is if we ever discover at least log to the fourth of log n to the fourth squares. That'll be a large stop. Or if we run out of squares to test, we'll also stop. And that'll be called an extinction stop. So the important thing is that we have this branching process, and now the amount of branching we expect at each vertex is at least 1. And so there's a chance that there's a positive probability that any exploration we do will survive. And so what we get is that for P of n in this range, asymptotically almost surely, there's a definite proportion, some alpha in the interval from 0 to 1, depending only on epsilon. A definite proportion of squares in gamma are contained in square components of size at least log n to the fourth. And so some definite proportion of our explorations will get to the large stop. And so we've got a whole bunch of squares that are in large-ish components. And at this point, the standard percolation framework will tell us that, well, okay, so we now do a little bait and switch and we say, well, we didn't give you all of the edges. We reserved a couple of them, and now we will sprinkle them on and we will try to join up components. we'll sprinkle in those edges, and we'll try to do them. We'll try to show that when we sprinkle in edges into gamma, that has the effect of joining up these largish components in the square graph. But we can't do that. And so it's our insistence on being induced that is the problem. And so we've got some square S here, and that square S doesn't have any diagonals. And so it's possible that when we sprinkle in an edge, we sprinkle in a diagonal to a square S. And that square S, right, in our branching process picture, it may have a lot of neighbors. And we just killed that square. And so we've kind of broke it. We have a possibility of also breaking up components of our square graph. And that's something we just can't fathom. We can't deal with. And so we need a different path to join up these large components. So what we do instead is instead of reserving some edges, we reserve vertices. And we sprinkle those vertices in rounds. And so, and in each round we show that, so if we have a component that's fairly large, C1, and let's say it's at least, log n to the fourth, there's some other component, C2, and there's some square S that we will end up sprinkling in when we sprinkle in our new vertices. We'll end up with new squares in the square graph. And those squares will start to join up our components. So we sprinkle in vertices, small amounts of vertices, and we do it in rounds because now we joined up C1 and C2, and maybe we joined up C3 and C4 with some S prime. But now in a later round, we might join up, now we have two larger components, and in a later round, we might join up these two larger components as we sprinkle in more and more vertices. And so, in fact, we are able to do that. And so for P of n in this range and for gamma sampled in GNP, we show that asymptotically almost surely, the square graph contains a component of size approximately n squared. And in particular, this is asymptotically almost surely a positive proportion that depends only on epsilon of the total number of squares in gamma. So there's some component that contains some definite percentage of the squares of gamma. It's giant by our standards. And we have this giant component now. It's not necessary that this component covers all of gamma. It doesn't follow immediately, but well, as with all probability, there's a rather technical argument, and we show that it actually does. And so the denouement is that for P of n in this range, asymptotically almost surely gamma sampled from GNP will have this CFS property. And when we combine this with our previous results with Mark Kagan, we get our main result that that square root 6 minus 2 times n to the minus 1/2 is a sharp threshold for the CFS property. And so it's a sharp threshold for quadratic divergence in right-angled Coxeter groups. And there are a whole bunch of open questions. This is sort of the beginning of a project, and some of this talk is advertising that cool things are happening here. So the first question we might wonder is, so Bearstock, Hagen, and Sisto showed that we have this dichotomy. Right-angled Coxeter groups are either relatively hyperbolic or thick. And so we want to know, is there a sharp threshold for relative hyperbolicity? And so our current state of the art is that we have a weak threshold. So a random graph gamma or a random right-angled Coxeter group will be relatively hyperbolic when the density of edges is much, much smaller than n to the minus 3/4. We are also curious about other degrees of polynomial divergence. Like, is there any daylight between relative hyperbolicity and quadratic divergence, at least generically? In a more combinatorial vein, we might our techniques we might be able to expand them to consider, instead of chains of squares, chains of other complete bipartite graphs. And then also just like, what other properties of right-angled Coxeter groups do you care about? And can you find a threshold for them? Or maybe even right-angled Artin groups, we could play the same game. And then finally, like, what if we use a different model of random graphs instead of this very simple Ernest-Renier model? So for instance, a random regular graph doesn't have enough squares to be CFS. Bolobash proved this. I don't know exactly when. But that doesn't prevent the right-angled Coxeter group from being thick or having polynomial divergence. And so so I'm pretty curious about this one and had an undergrad student that wanted to study it, but the model of regular random graphs is actually pretty challenging to get a handle on. So like, what can we say? If that's like sort of saying, what if we limit the number of relations that a given generator is allowed to be in? Can we say something about that group? It seems sort of pretty natural from a group theory perspective. Pretty interesting. Anyway, I'll leave it there. Thank you very much.
All right, thank you very much. Thank you for a very interesting talk. Thank you. All right, so now if there are any questions, you're welcome to ask them, please.
Okay, I have a question. So, like about, like you're talking about components of the square graph. Can you say when it is connected? Like, do you know P, any thresholds for that?
So that's a very good question. So the sort of model paper that we're working with, Bolobash and Riordan, they're looking at some other auxiliary graph and showed that it shows threshold for connectedness, and we weren't able to get that here because sort of our methods have to be a little bit different. And so that's a very good question, and we don't know the answer to it.
Mm-hmm. And you say other related graphs, like for example, I mean, okay, you have squares. What else can you like? Can you do triangles, or can you do like? Is it looks like squares is like it's essential? Like
yeah. So for us, squares is essential, and for our group theoretic motivation, squares are essential because they have to do with these flats, the system of flats inside of the right-angled Coxeter group. So Bolobash and Riordan were originally looking at a complex where each vertex is a k-clique, and you join two of them if they intersect in L vertices. And so this is sort of, they're using this as a model of network expansion. And so they've given precise thresholds for every K and L in this sort of massive paper that inspired us to do this. And they're asking a lot of the same questions at the end that you're asking, Olga. So they ask about precisely this question about squares. And they also ask about 5 cycles and higher cycles as well. So squares are important to us for the motivation. It would be more natural for us to think about chaining complete bipartite graphs together, because a lot of what we're doing is we're using the fact that a square is a complete bipartite graph to sort of figure out how to join up our components and things like that. But yeah, it would be natural from the combinatorial perspective to also think about 5 cycles, but we haven't thought too much about it.
Okay, thank you.
All right. Tim, could you remind me? I'm trying to remember now. There was some other context in which this CFS property came up for some other properties or some. It was used for something else, wasn't it? Maybe just a second. Sorry, I apologize. I've seen it maybe in your papers, some other papers, in some other results, and now I'm trying to remember what they were. Could you?
So definitely, right. I mean, so it's definitely appeared. So Donnie and Thomas have definitely thought about it just for quadratic divergence. Levkovitz also for quadratic divergence. I think there's sort of a question in right-angled Coxeter groups about which right-angled Coxeter groups are virtually right-angled Artin. And so the natural place you would look is the generating graph being CFS. Jason proved a couple of years ago that actually not all of them are virtually right-angled Artin. But I can't think of another context where it's come up that didn't have to do sort of, at least tangentially with this. You might have something with like the Laplacian, something with like some expander property, maybe. These are highly connected.
There was something else. Maybe I'm misremembering things. Never mind.
Well, Jason, are you still there? Have you seen?
Yeah, well, I mean, so it was related to this, though. I mean, you know, Hung Tran had written a paper where he was interested in the CFS property, but again, it related to, you know, this notion that maybe, you know, those are the ones where we know that there's quadratic divergence, so maybe those are related to Artin groups, and so then he's in various ways tried to understand what the geometry is of right-angled Coxeter groups that are CFS.
Mm-hmm. Right, and I think he had an additional assumption that they were planar.
Right, that now slightly rings a bell. Yeah. Okay. Thank you.
Yeah, and I think he wanted them to also be planar, if I remember.
Yeah, that actually. So now I remember it was actually something. For some reason, I remember it was something about planar CSF groups, but I don't remember now why. You know.
Right. It's a joint paper with him and Wynn, I guess. I think.
Yeah, and I'm trying to remember why they had to be planar. You know. So.
Yeah, I don't remember.
Okay.
Yeah, the point was they were able to give then a complete quasi-symmetric classification but they may have needed some other hypothesis. I mean, the point was the planar ones, once they were planar, then they knew that they could prove they were three manifold groups. And then, then it's kind of a special case of like this classification that Walter Neumann and I gave of graph manifolds. So they were able to kind of classify those QI types.
Oh, right, because yeah, they won't contain free cross free because they're planar.
Okay. Okay, very interesting. Thank you. All right. Are there any other questions? Okay. Well, let us thank Tim again. Thank you very much.
Thank you very much. Very interesting.
Yeah, very interesting. So I'll stop the recording now in a moment.